They have got their own limitations. To understand and put into a better use is a very important aspect of any of the technology. So here when I am defining about the forward problem, a forward problem involves predicting the effects of the outcomes based on known causes, system properties or inputs. So the example is, I am having an you are predicting the trajectory of a projectile based on its initial velocity and angle. So for a projectile, if I know initial velocity and angle, what is the direction it takes, I can predict. So this is a forward problem. So I know the inputs and also I know the system properties and also the causes. Then I will only be predicting the outcomes or the effects. So in the case of the inverse problem, it involves determining the causes, system properties or inputs based on observed effects or outcomes. So based on the observed outputs or the outcomes, you will be determining the system properties and also the what are the inputs which causes that outcome and also the what are the system properties or the determining causes which have resulted into that. So remote sensing is the inverse problem. So there you have got the signatures of the objects based on which you will be determining what is the type of the object which has caused that reflection and what is the properties of that object. So whenever you have got a forward problem, it is a straightforward and it's very easy. But whenever you have got an inverse problem, it is very difficult and it is very complex. And some examples I will give you. One of the project students of the Vjit has come to me and asked me, I want to do a project, a real-time project, really real-time project. I asked him what is the real-time project. He told really in time. So what is the really in time? I am having 2 months, I want to complete in 2 months in real time. So that is the meaning what he was having. And what you are going to do, I asked. I am having some senior projects, I would like to come from them. So what is the thing I am trying to tell here is, so he wants to do inverse problem. So he has already got the project with which he wants to formulate the problem and submit and then go ahead and doing the project, which will be very difficult thing. Understanding someone's written code is difficult than understanding the problem coming from the beginning. And another thing I will also tell you is, whenever you are having a project work for any of the BTech students, project work is nothing but formulating a problem and finding the solution for the problem in the framework of the project. But what will happen is, many of the times what we will do is, we will come from the solution. So you have a project, you formulated the problem, and for the problem you are finding the solution in the framework of the project. But when I start from the solution side, a problem can have multiple solutions. Similarly, if you start from the solution, you land into multiple problems. So that is the thing what is going to happen. And here, when we will be talking about the inverse problem, I am telling that this is the field where it is based on the, it is an inverse problem. So whenever you are studying about the what are the applications the remote sensing can have, you that will be limited by this inverse type of the problem. It will only will tell you based on the your effects what is the system properties, but it will not foresee what the effects will be caused by something as the input. So that's why any of the real-time monitoring thing and forecasting things, inverse problems will fail. But inverse problems will aid in coming out with the forward problem, which is very essential for type of the problems like prediction and so on. So that's why whenever you will be having a prediction type of thing, a landslide occurring, tsunami occurring, an inverse problem may not be suitable. But inverse problem inputs can be suitable for the by find out the solution and also do a prediction. So many of the time when we will be understanding about a particular technology, it's very important the type of the problem and the type of the solutions the technology will provide, so that you will be utilizing in its maximum potential the technological advancements and also the technological benefits what it can offer. But otherwise you will be always searching for a solution which that may not be offering, but you have to study it as a combination of the several other fields by formulating it as a forward problem and combination of the inverse problem and so on. And now we will be seeing about what is the key principle behind the remote sensing. So the key principle when we will be talking about the remote sensing is, as you already have seen, there will be an active sensors and also the passive sensors. The active sensors will have their own source of illuminating energy, and the passive sensors will depend on the sun's illumination for the reflectance from the objects. So the electromagnetic spectrum is one of the important aspects in the remote sensing. And then energy interactions, what will take place with the objects on the surface is another important aspect. And then sensors and platforms which collect this information and will provide is another important aspect. So these three will form the main important aspects of the remote sensing, and other, more advancements and more variations also we will be seeing as we will be progressing. So the main important thing one is the electromagnetic spectrum, which ranges from the gamma rays, ultraviolet rays to infrared rays in the visible spectrum, what we will be calling as Vjit, and also the gamma rays and cosmic rays to the radio waves on the other side. So the highest frequency what we are having is the gamma rays or the cosmic rays, and then followed by you have got the visible spectrum, which ranges from the 0.4 to 0.7 micrometers, and then as we will be going, the frequency is decreasing, and then we will be reaching towards the infrared region. So because of this reason, whenever you have got a very high frequency, as the wavelength is inversely proportional to the frequency, you will be having the smaller wavelengths. Smaller wavelengths, they can penetrate more, but they cannot travel and they will be absorbed by the atmosphere. So whenever we will be studying out the electromagnetic spectrum, it will give us an information what is the wavelengths which are useful for doing the remote sensing, and what are the wavelengths or the electromagnetic waves which you can make utilization of doing a remote sensing and determining the properties of the object. So when we will be talking about the forward problem and reverse problem, when I want to formulate as an inverse problem and find out the properties, what will happen is there is one boy who has been sent into a room. That room is very dark and closed, and everybody asked him to find out by going inside the room what is there inside. So one boy went and he hold up something which was looking like a pillar, and he came back and told there is a very big pillar inside. And another boy went again, and then he hold some part in the room, and then he came back and told there is a big rope inside. And similarly one more boy went, and then he hold up something, and then he told there is a very big flaps which are there inside the room. And then after coming, all the boys have come out of the room. When we see the object what is there inside, there was a very big elephant. So one who has touched the legs of the elephant, he understood it as a pillar. One who has touched the tail of the elephant, he understood it as the rope. One who has touched the leaves, the ears of the elephant, he understood that there are some very big flaps and that sort of thing. So the inverse problem will also give you this type of the experience. So you touch some wavelength, it will tell you something. You touch some other wavelength, it will tell something. And if you touch the physical properties of the object, it will tell you something. And if you touch the chemical properties of the object, it will tell you something. But if you combine everything, then you will come to the what is the object which actually it is. So that's why when you formulating an inverse problem, it is a complex in the sense that whatever is the aspect you access, it will give the information about that aspect only, but it may not give the complete picture of the object which you are going to study. And similarly, when we will be talking about this electromagnetic spectrum, all the objects, they will observe some wavelengths and also they reflect some wavelengths. For example, if you are seeing a tomato observes all the other wavelengths other than the red. The very peculiar fact of the life is, let's say you are a very fair person, you are looking very white. Is it not? I like because you are fair, you are white. But the very fact is that your body doesn't like white, that's why it is reflecting back. And similarly, tomato. I like tomato because it looks very red. I like apple because it looks very red. But the very fact is, the apple by itself, the tomato by itself doesn't like red. That's why it reflects back. That's why you are seeing it as red. So that is the irony of the life. So you like something, but that may not be liking that itself. So the electromagnetic spectrum is something which will absorbs, reflects, and also transmits the various types of the wavelengths and giving the different properties for the objects what you will be encountering. And when we will be seeing about the electromagnetic spectrum, there are reflecting the colors or the electromagnetic wavelengths which are causing a particular color to an object and also the texture to an object. But when we will be talking about the texture, it is a physical property of the object. So there are various types of the sensing mechanisms which you will use for determining the physical properties and also the chemical properties of the objects. For example, if I want to determine the chemical properties of the objects, I may use the electromagnetic spectrum and optical remote sensing. And if I want to determine the physical properties of the object, for example the texture and also the smoothness and so on, I may use the radar and microwave signals for determining the physical properties of the object. If I combine both, I have got the physical and chemical properties of the object, which may give a complete understanding about the object which is under observation. Is it not? So many of the times what will happen is, when you are addressing the inverse problem, it is like an elephant in a dark room. Whichever part you access, you get an inference which may not be the truth. So when we will be having the electromagnetic interactions in remote sensing, we have got basically the 5 types of the interactions, like the reflection, absorption, and also the transmission, scattering, and emission. So that important thing is the scattering. Types of the effects in the various types of the objects. For example, it causes the blue skies, and also it causes the clouds white. And then when we will be talking about the reflection, there are various types of the reflection. So the main important thing of the any of the inverse problems or remote sensing is, I am having an object under observation, but the reflectance what comes from the object may not be by the object alone. For example, I am having a tree and beside it ground. And when I get a reflection from this, it is maybe tree leaves, tree trunk, and also the ground and so on. So a pixel may not be an impurity, a pixel of a particular object, but it can be a mixed pixel. So the amount of mixed pixels, what can be there in image based on the resolution, are going to outperform the pure pixels, what are going to be there in the image. So which limits the accuracy with which you can determine the properties of the reflected material, or the what is the object which has got the reflected a particular type of the light. So many of the times what will happen is, knowing about the limitations is also very important thing. For example, I will tell you an example. A boy was asked, "What do you know about the AML?" And he told he learned about the AML at that time. And then he told, I know everything." So the important thing is, another boy was asked about the AML, and he knows what is the development, what has taken place, and what is the current developments which are happening. Then he told, "I know very, very little. I know only definition. So it only matters. Somebody tests, I know everything. Or somebody tests, I know only something. It matters on the subjectivity of the person as well. What the amount of the subject depth he has got. So if you know the what is the depth of the subject, you may tell, I know very little.
And if you doesn't know whatever you learn, that itself is subject if you feel. You will tell, I know everything. Is it not? So likewise, when you have got these type of the things, the inverse type of the problems of the remote sensing, the object what you will be determining, you may not be able to determine at 100% accuracy at any point of time because of this mixed pixels, some separation of the mixed pixels, and so on and so forth. So with respect to that, many of the times what will happen is, let us say I determine the particular object and its characteristics 80% accuracy, 90% accuracy, still that will be good enough. And similarly, when you have got the machine learning or deep learning types of the algorithms, it is not the panacea for every problem, and it is not the solution for the every problem. And you also need to understand many of the times machine learning may not give good results, especially when your data is not robust. Machine learning algorithms are data driven, and if your data is not robust in nature and it's going to vary too much, then you may land into overfitting or underfitting problems. And also, many of the times, what will happen is, let's suppose I am having in a B-Tech of type of the project, and if a boy has come to me and asked, I want to build a project, to suggest me a good project. And what will happen is, there are various types of the projects how we can classify. For example, if I want to do a new invention itself, there is an GR processor. We would like to invent beyond GR processor. So then it is not a project, but it's an invention. This is the first category. Second one is I'm having an 8085 processor, and it supports the three modes of operation. But I could able to find that these three modes are insufficient for a particular application. I would like to have a new mode which is going to serve for this application. So this is another one which is an incremental type of the project. And the third one is I am having an 8086 processor. I am going to implement a similar processor because I don't have the technical know-how, but still by studying its functionality and also its properties and everything, I rebuild or I have made a model of the 8086 processor. This is also a good project. And another fourth category of the project, I brought already someone done project and then I started understanding that and then implemented my own way. This is also a good project. Understanding somebody's thing and implementing on your own is not an easy thing. But the other category of the project is I simply bring some other project and submit. So this is a very dangerous thing. So similarly, the thing what I'm trying to tell is so when you are having the determined objectives and also the different determine the properties of the object which are causing that reflectance, you are not going to get a 100% accuracy, but still 90% of the accuracy and also the algorithms what you are going to use, not necessarily the algorithms which are people are fancy, but the algorithm which is sufficiently addresses the problems which are involved in that is going to give good results. So when we will be talking about the emission, which is mostly in the thermal infrared region, here you are seeing the red color of the city regions where a lot of emission takes place and which have been captured by the satellite. And then we'll be talking about the key concepts in remote sensing, which is one is the radiance, which is the amount of radiation leaving a surface in a specific direction per unit area, and then irradiance, the total radiation received by a surface from all directions, and then reflectance. And generally, the satellite the images what we will be acquiring will measure the reflectance, which is the ratio of reflected radiation to the incident radiation on a surface, and it is a dimensionless. And the important thing what the remote sensing will use for determining the properties of the object which causes a particular reflectance is the spectral signature. The spectral signature is a unique pattern of reflectance or absorption or emission across different wavelengths for a particular material. Every material in a given wavelength, we have different types of signature based on which you will be determining whether the reflectance has come from a water or it came from the agriculture fields or the vegetation or maybe from the urban areas or from the land. And similarly, the here what you are seeing is there are three types of the spectral signatures. One is the green, which is nothing but the vegetation. What you are seeing here, that blue band will start from zero point 0.42 to zero point 0.5, and then I am having the 0.5 to 0.5 6 around, I have got the green band. And in the green band, I am having an increasing reflectance in the of the vegetation in the green wavelength. And as the red wavelength starts, it slowly starts decreasing. And again, when the infrared radiation starts, it increases and reaches the peak value. So that's why vegetation has got the good response in infrared region for the different types of the factors. And then I'm also having the soil, and this is the red wavelength, which is starting from 0.62 to zero point 0.8, zero point 0.7. And then here you are seeing the red wavelength is increasing, and then after zero point 0.7, it will start decreasing. So in this case, it also gives an signature of the red wavelength, what they will be saying for the soil. And the application of the spectral signature, they will be used for the identifying plant health and also for the water quality, mineral mapping, and other types of the applications for the agriculture and also the urban studies for finding out the built-up areas, differentiating between vegetations, various types of vegetations and the plants, and also for the water. And then all this is possible. You have got electromagnetic radiations and you have got spectral signatures from the different types of the objects. And when you have got the electromagnetic radiation and the radiation by the objects, there needs to be a certain window which will make you to reach the sensor. The light has to come from the space, and also the reflected light has to reach to the sensor. And this is made possible by the various types of the atmospheric windows. Not all wavelengths, the atmosphere is transparent. For some of the wavelengths, atmosphere is opaque, and it's not going to allow the various types of wavelengths. For example, for gamma and X-rays, atmosphere is totally opaque, so nothing will come from the atmosphere. Nothing will come from the space, and also nothing will go from the earth to the space. And for the visual wavelength, it is transparent. And also we have got the water absorption bands and followed by the infrared windows and also the microwave windows, which are going to facilitate the infrared or thermal infrared imaging and also for the microwave imaging. Well, these things I think you have already seen, so I will not spend much time on this. That's the only pursue. You have got active remote sensing and passive, where you have got the for the active radar itself will send the signals and receive, and for the passive you have got the sun. And aerial versus satellite remote sensing, when you have got the aerial types of the sensors, you will have the huge amounts of the data, which because the spatial resolution is very high, and also have got the multispectral versus hyperspectral. So when you have got the hyperspectral sensor, they acquire data in many narrow contiguous bands, so allowing for the finer discrimination of the materials. So what is the main principle here is wavelength is an source of information. Then more the number of the wavelengths you will be having, information will be more. If I acquire in the black and white image compared to a color image I have got the three bands of information. Each band is an information, and whereas in the monochrome image, you have got a single band. So, information wise, a multispectral or hyperspectral is much, much more superior than a panchromatic image. And now we'll see the four arts which are very much useful in the remote sensing. One is the spatial resolution, which is the smallest object which is distinguishable, which is the size of the, which depends on the size of the CCD array and the viewing angle and so on. And another one is the radiometric resolution, which indicates the ability of the sensor to distinguish between different intensities within a respective wavelength range of a channel. So, simply speaking, when I am saying 8 bit, I have got the 256 levels. And if I am having only 2 bits, I can have only 4 levels. By using 256 levels, you can represent more intensities than by using only 4 levels. Is it right? And similarly, spectral resolution. If I am having the more spectral bands, I have got the more information. And if I am having an few spectral bands, the information compared to the hyperspectral type of the sensors is less. So the spectral bands will tells you about the spectral resolution, how much spectrally you are resolving a particular type of the object in a spectral wavelength. And there is another parameter for the remote sensing images, which is a temporal resolution, which will tell you about how often you can visit a particular portion of the earth at different points of time, which will tell you the temporal relation, which is very much important for the time series studies. And then remote sensing technologies, when you have got a sensor, the main important thing is if it is an optical sensor, you have got an CCD or CMOS type of the arrays. It can be an line scanners or line sensor, or it can be an area sensor. So in the case of the area sensor, it will take a snapshot of the area. And in the case of the line sensor, you will scan as an push broom type or whisk broom type, and then covering the entire area. And similarly, you have got the radar sensor, which will use as the synthetic aperture radar for resolution enhancement by using the same antenna. And then you have got the LiDAR, which is a short form for the light detection and ranging. It aids in applications such as forestry and urban planning. And then satellite systems, we have got the various types of the satellite systems from the foreign as well as from the Indian. From the Indian, we have got the Indian remote sensing series of satellites, which will support for the various types of the satellite-based applications. And we have got the navigation satellites in the form of the Navic and also the GPS and Galileo. And then you have got the communication satellites of insert series of communication satellites, point-to-point communication and terrestrial communication, and also the broadcasting type of the communication purposes. And then we have got the data acquisition methods, the satellite remote sensing, which will and satellite will be placed at polar orbits or geostationary orbits. And then when you have got the aerial remote sensing, which will be at a lower altitudes, it will fly, and the area of the coverage will be less, but at the same time, we will have the very high resolution images. So these are very important technologies with respect to the applications, what you can put in terms of automating and then doing the predictions with respect to the utilization for the community at a larger scale. For example, I'm having a drone of the aerial data from the various types of the fields, which you can utilize, and also you can alert for the various types of the diseases what can happen in the field, or you can monitor the growth of the crop, and you can estimate the crop yield and so on, and also aid for the smart city planning and also the smart city modeling, and also for the various types of the navigational purposes. For example, you are seeing the Uber and other type of the things. As soon as you put your starting point in the destination, it will show the route very properly without any error. So those types of things also you can have the data, and on the data which has been geocoded, you can provide all the information even for the communications and also for the navigation and also for the traveling. And you have got the ground-based remote sensing, which is also used for the calibration and that type of the activities, and also for the all the instruments what we will be utilizing in the remote sensing needs to be well calibrated so that the data will be robust across the conditions, across the seasons, and across the viewing angles, across the sun illuminations. So once the data is robust, then only you can put into use for various types of the applications. Is it not? And the other part of the remote sensing, once you have got the reflected ray light, which has been recorded by the sensor, and an image has been formed, the next part will comes the data processing. The image acquired by the sensor has to be made suitable. Okay, this one. So the image acquired by the sensor has to be made usable so that it maps the area of the ground for which you have mapped. So for the area to map, the area information and location of the area, all those things you have to assign to that. So that's what exactly will happen in the form of the radiometric corrections, geometric correction, and also the atmospheric corrections. In the radiometric corrections, it will be adjusting the data to correct the sensor noise and variations. And in the geometry, you will be aligning the data to a coordinate system so that if I say I'm at Hyderabad VJIT, I have to be in VJIT. So this has got a latitude and longitude information, which has to be correctly coded onto the image. That's what exactly will happen in the geometric correction. And then the atmospheric corrections, the atmosphere is not free. it is filled with haze and other types of the particles, the scattering and so on, which needs to be corrected. That's what will take place in the atmospheric correction part, so that the reflectance what you have got, it is the actual reflectance of the object, not by the affected by the atmosphere. Image processing techniques, when you will be using any of the pre-processing for any of your applications, whichever involves the image, we will be passing through some stages of the processing, and basically there may be image enhancement, and then it may be image transformation, or it may be image segmentation. So the image and transformation, many of the times you will do for augmenting your data sets. Whenever you have a limited number of samples for training, I would like to do a transformations on the data set, and then augment the data set with number of samples which I can use for training the model. And then data integration and interpretation. So we have got the various types of the integration methods. Like when I am having a fusion, so there is a data fusion methods, and also the integration with the geographic information systems and so on. And we will be seeing the advancements what has happened over the years. It is ICT, Information and Communication Technology. Now it is GeoInt. So it is a geographical intelligence system. So the GIS and the AI both have been combined. Now it has evolved as a GeoInt. So in the coming days, we will be listening more about the GeoInt as a buzzword, which has got a lot of potential for transforming the society into a very nice living place with respect to the transportation, and also with respect to the communication and so on, and also the infrastructure facilities what the thing can provide. And another one, what I would like to uh, 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 bring all of your attention is, let us suppose I am having a satellite system which is placed in the space, and it has provided the image. The image is not free from the various types of the atmospheric disturbances, and also the various types of the sensor degradations and so on and so forth. So there is a concept called the digital twin, which we have done to an image. So digital twin is building a digital equivalent of a physical system. So when I build a digital twin, what will happen is I need not have to do any experimentation on the physical system. I will do on the twin, and then whatever the effects it will come encounters, all those things and the remedies for those I can implement on the image. So what will happen here is, let us suppose I build a digital twin on a image of a particular area. So next time, whenever the satellite goes through that area, whatever the degradations or the problems that can occur, let that be there can be a cloud or some portion of the image, and there can be a striping at some part of the image, and there can be atmospheric noise at some part of the image. But because I am having the twin, now I will update only that portion of the features which needs updation, and all the other things in the form of the noise, striping, and also the cloud, I'll discard, and down my digital twin is free from all the noise on that particular day, though the satellite image has got the various types of the problems like the noise, cloud, and so on. So that is the advantage of the twin. And when we have got the an image, always you will be having a cloud-free image and a very nice image at any point of time. If I build a clean twin for a particular area, so that is the emerging applications what you can also can think of, not only for the medical field, where a person's twin will be constructed, and also in the automotive industry, where a process twin will be constructed, and all the experimentation will take place on the twin. So in the future, you will be seeing more twins in terms of the AI and ML, in addition to the generative AI models, which will be going to be very handy in terms of getting an quality data and also the quality outputs. And there are various types of the applications with respect to research, remote sensing, like agriculture and forestry, water resources, mineral exploration, and also the, as morning madam was telling, yield estimation, and also the yield enhancement and so on. And also for the environmental monitoring, for studying the climate change studies, disaster management and pollution tracking, and transportation planning, land use and land cover mapping, infrastructure development, and so on. So this I will anyway. This the only two three things I will touch upon, like the sensor limitations. So there is a limited resolutions and limited number of sensors. Many of the times, what will happen is if I want to study a particular area over a period of time, and then bring out the insights of that particular area, I need to have the several coverages or maybe one coverage at least every day. So there is a limitation of the sensors, and also when I am having the more number of the spectral bands, the more the information I am having. So hyperspectral type of the sensor at a very high resolution is another important challenge with respect to sensors. And also when you have got the hyperspectral type of the sensor with 256 bands and 300 bands and so on, the volume of the data what it can generate is very high. And then how you can manage that is also another important thing. And then the real-time data processing. So this I will keep, and then this also will keep. This is also not required. Okay, then I will go to this. Yeah, yeah. Yeah, yeah, sure, sure, sure. Yeah, yeah. We'll study. We'll study. Hmm. We'll study. Yes, yeah. Not a problem. So having seen the remote sensing, so it's a property of remotely without being in touch with the object, determining the properties of the object. And this determining of the properties of the object is useful in many ways, like what you are seeing. The main important things on the land or on the earth is water, land, and also food. So the food that comes from the plants. So the plant monitoring you can do with the remote sensing, and the drinking water management, and also how you can see that the drinking water is going to remain and it's going to sustain. All the things you can also can study, and also can make the actions and actionable plans for preserving the drinking water areas. And then other one is the land. How much land has been used? How much land has to be is vacant? All those these classifications you can make. So the very important aspect with respect to remote sensing is it is going to make your life very happy, and also it's going to provide all the facilities which is going to make your life much more easier on the planet Earth. And also it will also preserve and pass it on to the future generation. So that is the importance with respect to studying the remote sensing. Also, the images, what you will be doing. Let's suppose I will be doing various steps of the AEML applications. For example, I will do super resolution. If I give you a picture, I will do makeup and all those things and apply the filters, and I will generate a very beautiful girl. And similarly, I'll reduce your age and generate and so on and so forth. But these are not going to feed you because after all, you have to preserve the land, water, and also the food. So after these three only the filters, all those things will comes into picture. So that's a very fundamental aspect. When you are working on the things, some things which will improve the standards of living of the humanity is the thing what is the important one. So here also you have got the images. Once you start working on these images and providing the solutions with respect to the transportation and with respect to the preserving and also the making the yield more from the plants and also from the vegetation. And also you can make the better use of the land what is available on the earth. These are all the very important and very fundamental aspects. When you touch upon this, when can make models and that sort of things, then it's definitely is going to change the total facet of the humanity as a whole, not only for us. So that is the importance when the remote sensing has got with respect to the conservation of the natural available resources and also the planning and also the managing of the natural resources. So with respect to that, now I am going into how we can classify the various features on the earth, and also how you can make the land use land cover maps so that you can conserve the area on the land and then also make the better planning for utilization of the various resources on the land. So here I am having the two types of the classifications. When we will be telling about the classification, next I will show the other aspect. So the classifying the image into predefined categories is what will be broadly will tell about the classification, and also identifying the objects and features in the image. And there will be various steps of the applications. And then another one is very important thing what we will come across is the key differences between classification and regression. So when we will be having the classification, it outputs discrete labels and discrete classes, and total image into a discrete number of classes. But when we will be talking about the regression, it outputs a continuous values. And there are various steps of the classification algorithms and also the regression algorithms. So the regression and classification many of the times looks similar in nature, but the application of them has got the different purpose. Like when I'm having a classification, a classification problem can be formulated as a regression problem, and a regression problem also can be formulated as a classification problem. Both are interchangeable, but the outputs what they are going to give, based on that, the accuracy what you are going to get and what type of the problem you have to formulate will depends on. But for example, if I have classification problem, but if I formulate it as a regression problem, still I can formulate and can run. But the thing is, the output what you are going to get is not going to be that much accurate what when you do a classification problem. So these two are the very important things what you will be coming across in the AML, the classification. It can be a supervised classification or it can be unsupervised classification, and it can be using a support vector machines. It can be using a CNN based architecture. But the thing what you are going to classify and what you are going to regress has got much more significance than application of an AML algorithm. And the various types of the algorithms for the classification, you've got the convolution neural networks, support vector machines, ANNs, and decision trees and random forest. And similarly, when you will be going for the image regression, I am having the linear regressions, polynomial regression, neural networks and deep learning, even for that, and Gaussian process and other models, which will provide the probabilistic predictions. So this is with respect to difference between the regression and classification. Now, with respect to the image classification, what a traditional remote sensing the application user will apply, and what are the various types of the algorithms, just I will demonstrate here. So there are the two types of the classification, supervised and unsupervised. The common decision rules in the supervised is the parametric decision rules, which is a minimum distance classifier or centroid classifier. And another one is the maximum likelihood or Bayesian classification. The maximum likelihood classification will provide a very good accuracy with respect to the classification outcome. And then non-parametric decision rules, we have got the parallelepiped classifier and also the feature space classifier. And on the unsupervised classification, you have got the clustering mechanisms. The very important clusterings are the most popular clustering mechanisms are being the K-means clustering and ISO data clustering. That I mentioned here, but we'll go inside. It will give some more insights into what is the classification, why you need to do a classification, and how you can classify the entire image and then come out with the various types of the statistics, which are very important for the land use land cover analysis and also for the vegetation analysis and so on and so forth. So image classification is sorting pixels into a finite number of individual classes or categories of data. As you are seeing here, here I have classified this continuous image into 8 classes. When once I will classify, now it's not more a continuous raster image, but now it is a thematic image. So it has been organized into 8 teams, and this is a vegetation team. And within the vegetation and water, I have got the various types of the classes, deciduous and pine and so on. And once you do a classification to image, this is how the output of the classified output will looks like. And many of the times it derives the thematic information from spectral information and reduces data volume and permits analysis of the features. So this is the purpose of the classification. So it derives the thematic information from the spectral information. So here, as you are seeing here, there are clusters of data from different surfaces. Now, as you are seeing here, there are six classes: corn, forest, hay, sand, and so on. So all these classes have been arranged as the clusters. As you are seeing here, there is a band X and band Y. If I draw a line from here and a line from here, the signature of the corn is somewhere here. The cluster of the corn is here. So like this, for different signatures, they will form different clusters in the feature space, which will be utilized for doing the classification of the features which are there inside an image. So when we will be doing the classification, there are very two important aspects. One is the information class, and the other one is the spectral class. So the information class, as an interpreter, when I see the image, I need to identify what are the various types of the features which are there on the image. For example, water body and also the vegetation and so on. So when I will mark those features as an information for the computer for doing the further classification, that is called the information class. So it is a class specified by an image analysis and it refers to the information to be extracted. So when I am having in the big image, I will show these are the four or five types of the classes. And I will also will tell this is the sample of a particular class. And based on the sample, what I will give, and the computer will perform the classification. So that will comes as a supervised classification. So I have provided a supervised sample set to the computer and it has classified. So it is supervised classification. So when I use the information class, the classification is supervised classification. When I use the spectral class, it is a class which includes similar gray level vectors in the multispectral space. And spectral classes are group of pixels that are uniform with respect to their brightness values. So there are spectral vectors in the multispectral data. And then by using the similar gray value spectral vectors, I am grouping them and then doing an cluster and doing a classification. This is an unsupervised classification. If I use a spectral class, then it is an unsupervised classification. If I use the information class, then I am trying to do supervised classification. So supervised versus unsupervised, and supervised is based on the information class. So because the class is derived by the image knowledge, so what he has to provide is the supervised training set. So for the supervised classification, user provides the training set, and for the unsupervised classification, it is automatic. The computer will perform the classification, and the only thing what you have to do is how many number of classes you would like to classify. So if you have a set of desired classes in mind, then create the appropriate signature for the data. For example, I am having vegetation, water, urban area, land, and so on. Then I create those information classes, and then we'll tell the computer these are the information classes from the image what I have identified. Based on this, you further classify. For doing that, there are various steps of the algorithm, what we are going to see. And then in the unsupervised this classification, it uses the spectral class. It is the spectral properties or gray level properties of the pixel values. And based on the similarity of the pixel values, it will make them as the clusters. And those clusters will be classified into the classes what you are going to specify. So these classes are be determined by spectral distinctions that are inherent in the data. And then training for the classification. So first step for the first step is the identification of the what is the type of the classification you would like to do, supervised or unsupervised. If you want to do a supervised, you provide the information class, and if you want to do unsupervised, you do provide the spectral class. And then once having done that one, when you are going ahead with the supervised classification, the information class has to be identified. That's what we'll be calling it as the training for the classification. So in the supervised training, it is controlled by the analyst and select a pixel that represents patterns and more accurate but requires high skill. Because as the end user, you need to have the ability to distinguish what are the types of the features which are there in the image, water, vegetation, and so on and so forth. And so in the case of the unsupervised training, it is computer automated. You only need to specify number of classes and how many number of iterations you want to perform. And the computer uncovers statistical classes, but it is less accurate and less skills are required. So this is the classification workflow. I have got the raw data. I do a pre-processing. Pre-processing is nothing but the removing the atmospheric effects so that your data is more robust with respect to the spectral signatures and also the gray values. So once you have got the pre-processed output with respect to atmospheric corrected, then do a signature collection if it happens to be a supervised classification, and then signature evaluation, and then perform the classification. And when we'll be talking about signature, for the supervised classification, information class is nothing but what we'll be calling it as a signature. So the signature is nothing but, let's say I'm having a lake. I draw a small polygon and tell this is the lake. And like that, I can go ahead for identifying the different types of the features. Like I draw a polygon and will say forest. I'll draw a polygon and will say agriculture. And also I'll draw a polygon and say river. So a set of pixels selected to represent each primary land cover. Land cover is nothing but a land is covered with various types of the types like the vegetation and also water and so on. So that's what we call it as the land cover. And here also another example for identifying the signatures from the image. I put the various polygons and identified the various signatures, which are part of the training set or part of the my information class, which I am going to submit to the supervised class pair. So supervised classification at the training stage, as he identifies the training areas and develops a summary. And classification stage, each pixel is categorized into a land cover class. Either it can be in water, it can be vegetation, it can be a land, it can be a settlement. And at the output stage, the classified image is represented in JS or other forms as a thematic map. The basic steps, what already we have seen the image data set, training stage, classification stage, and then the output stage. And this is one of the example for the data which has been classified into these many classes. Like each color represents the type of the class which it has been classified. And now when coming to the supervised classification algorithms, there are two types of the algorithms in the supervised classification: parametric decision rules and also the non-parametric decision rules. And in the parametric decision rules comes the minimum distance classifier or the centroid classifier, and then maximum likelihood or Bayesian classification. Non-parametric decision rules, I have got the parallelepiped and also feature space classifier. So when minimum distance or centroid classifier works is, let us suppose I have selected the various types of the signatures. And all those signatures, they will be spectral distance between the candidate pixel and the mean of each signature will be calculated. Let us suppose I have identified 5 signatures: land, and also the vegetation, water, and so on. For all these signature, mean vector will be calculated. Once I calculate the mean vector in the feature space, they will come at some portion as in cluster, suppose. And for this cluster, I calculated the mean, and rest of the image I have to classify now. I have got only training set of a few places. Rest of the image now I have to put one of the class. For that one, I will use minimum distance or centroid classifier. What it will does here is, let us suppose this is the candidate pixel, and from this pixel, distance will be calculated from the mean vector of the each signature. So you have got the information classes, let us say 5, and distance from the candidate pixel to the information class centroid will be calculated. And then whichever is near, whichever has got the minimum distance, it will be classified into that class. So let's suppose here, this is the class which is the minimum distance with this. So it will be classified as this class. Pardon? Yeah, yeah. There are some variants with respect to this also. That I will be covering this also. You can use the fuzzy type of the things also. But many of the times, what will happen is the minimum distance will works on the based on the calculation of the average of the say your signature what you have collected and finding out the minimum distance. There are other variants of the classifiers. Fuzzy means classifier and fuzzy C classifier and so on, which are also advanced version of the fuzzy type of the classifier. And then when you will be having the minimum distance classifier, it calculates the mean of the spectral values in each band and for each category. Measure the distance from a pixel of unknown identity to the mean of each category and assigns the pixel to the category with the shortest distance. And if it finds unknown if the pixel is beyond the distance defined by the analyst. So I also will be defining, let us suppose I am having a certain distance. If it is within this distance, you put into this. And if it is beyond that distance, it will classify it as an unknown pixel. And also this is what the minimum distance of centroid classifier output final will looks like. It has classified into different uh, uh, clusters, and each cluster has got the type of the class, what you have already gained in the training set. So this is another example. This is the pixel, and this has got the minimum distance with respect to this class. So finally, this pixel will be put into this class. And the advantages of this one is it is computationally simple and faster, but disadvantage is it is insensitive to difference in variance among categories. And for overcoming this, we have got the maximum likelihood classifier, which evaluates both variance and covariance of the trained spectral data set and deciding the candidate pixels class. So to do this, the classifier assumes that distribution of points for each cover type are normally distributed. So there are certain assumptions with respect to this classifier. But this classifier has got the highest accuracy with respect to classification. So the distribution of a category response completely described by the mean vector and the covariance matrix. What it will does is it will compute the probability that unknown pixel will belong to a particular category. So here I will be showing here. So probability functions are calculated for each training inputs, and from based on this, probabilities are it will be assumed that all the classes have got equal probabilities, and a candidate pixels probability will be calculated, and whichever matches with the signatures probability, it will be put into that. So that's what exactly the maximum likelihood a pixel can fall into one of the classes. What will be calculated based on the probability, and it has got the highest accuracy compared to the minimum distance classifier. And another one is a parallel piped classifier. It is based on the, let us suppose I have collected 5 signatures. Each signature has got the minimum and maximum. So based on the minimum and maximum, a parallel piped in 3 dimension or multi-dimension will be constructed. So it is sometimes called the multiplane classification also. So, and when you have got the n number of bands, so my parallel piped will be there in those many dimensions. So the minimum and mean of each band will decide you the type of the parallel piped what we will get, and the candidate pixel in whichever parallel piped it falls will be classified into that class. And it falls it is assigned pixel to the where the pixel falls in. And another important classifier which is better than parallel piped classifier is the feature space classifier. Instead of constructing a parallel piped, what it will does is it will generate an polygon of a size which will be following the signature vectors what are there in your training data set doing the classification, which is more accurate than the parallel piped. And then one coming to the unsupervised classification, you have got the various steps of the clustering mechanisms. Here there is no training set is required. You only have to have the spectral classes, which is nothing but the brightness values of the pixels. But what will be what one important thing when you will be doing an unsupervised classification is data needs to be robust. So for making the data to be robust, you need to remove all the types of the distortions what are associated with the data in terms of the atmospheric and so on. So once you have done the atmospheric corrections and so on, now whatever the results you are going to get is going to be more accurate than without doing the atmospheric correction. So there are various steps of the clustering mechanisms. One was sequential, was statistical, and then RGB and so on. But main important things are the K-means and ISO data clustering, which are mostly utilized by the all the analysts. So in the case of the unsupervised classification, you are not going to assume any previous knowledge about the data because you are not going to collect any training on the signature data. And then it tries to spectrally separate the pixels. User has controls over initial cluster values, number of classes, and number of iterations. I will tell to the computer, I want to divide, classify this image into 5 classes right, in this many number of iterations. That are all the two inputs what you are going to give, and rest of the things will be done by the computer. So that's why it is an unsupervised classification. The general practice is what I would like to do an unsupervised classification, which is nothing but the clustering. Once I have got the data into some clusters, now then apply the supervised classification on the clusters. So that's going to give more accurate results. So pixels change threshold, which also we are going to give, which will be decides the maximum number of iteration has been reached or not. So to explain this process, just I will show demonstrate here. So here I am having the DN values. I applied the spectral classes and the algorithm has been applied. It has put into the different types of the spectral clusters, A cluster, B cluster, and C cluster. And then it has classified the image into 3 types of the spectral signatures: water, agriculture, and rock. And in the case of this, first I will select a random selection of pixels from a cluster of centers, and algorithm finds the distance between the pixel and forms the initial estimates of cluster centers. What I will do in the unsupervised classification is first I will select an initial seed of a clusters. Let us suppose I am having 5 clusters. I will select the 5 clusters and the algorithm initiates with randomly selected 5 clusters. And then it will find out the mean of each signature. And then once it find out the mean of each cluster, then it starts doing for the rest of the pixels putting into one of the clusters. So once it puts the pixel, then again it calculates the mean. And whatever the changes it will find out, then readjust the clusters. Like this, it goes on by adding the pixel, recalculating the mean, and then readjusting the clusters till the final iteration. When I will calculate the mean, there is no difference from the previous step. So once when there is no mean difference from the next classification to the previous cluster, then that will tell us that your clustering is complete. So what I'm trying to tell is, let us suppose I'm having an image. I want to divide into 3 classes. I will tell the computer, you do 3 into 3 classes in 10 iterations. Then computer will initially starts with the 3 random clusters and then calculates the mean of these clusters and tries to put the rest of the pixel values into one of the cluster. One round it will does and then again calculates the mean and then again reclassify these clusters into different 3 classes and again we'll put the pixels and it will do these iterations. The next iteration and the previous mean are not going to change for the next iteration and the previous mean value. So this is the one of the unsupervised classification where you are seeing here. Though this is a water body, even it picks up the various types of the things because it's purely based on the gray value rather than the original content what is there. So unsupervised classification is totally automatic and computer is going to perform based on the gray values what are there in the image. So it's going to be much accurate with respect to the classes, but with respect to the interpretation of the features, one has to analyst has to associate with that. So really tell what type of the features they are. For example, here the entire thing is looking like a water, but it also shows some uh, different types of the gray value which is occurring here. And similarly here, this is and it looks like a similar feature, but it will also will show the variations what are there in the gray values. But I would like to classify the total thing as a similar feature, is it not? I don't want 2 classes in within the same feature because of the gray level difference. So that is the practicality versus the what the algorithm will does automatically. So many of the times, practically classifying an image, you will have the exact idea of the what type of the feature it is. But when you do an unsupervised classification, it also will takes care of takes into consideration all those variations, which also may belong to the same class. Many of the times, what will happen, Vada, when I am having a gray, when I am telling about the gray scale, Grayscale has got single band. But when you have got a color image, you have got the multiple bands. Multiple bands is more information. More information will make your results more accurate. And if I use a single band, the gray level differences, let us suppose 8 bit, I can classify into only 256. But if I am having a 3 bands of 8 bit, 2 to the power of 8, not only 2 to the power of 8, and into 3 bands, that many number of classes you can have. So spectral separability will be much more in color images than in the black and white images. Black and white images will be defined by your radiometry, but here I can have 1.67 million colors within a free bands if they have got the 8-bit data. So 1.67 million classes I can have, but in this case only 256 will be limited. So mostly people will be doing the classification on the multispectral images only. Though for the convenience sake, we may explain that the grayscale. Grayscale implies for the color also a single band is a grayscale. So when I will be having the unsupervised k-means and also the ISO data, the only difference with ISO data algorithm is the previous whatever I explained for the k-means. Compared to that, in the case of the ISO data algorithm, it also does the further refinements by splitting and merging of clusters. So for example, I am showing here. So this is the cluster which has formed. And if I calculate the mean of the cluster, sometimes it will be as the cluster grows, the mean will be more than the distance. So in that case, what it will does is it will split this cluster and then redistribute so that all the cluster will have the equal representation. So that is only the difference with respect to the ISO data and also the k-means classifier. Anyway, this is the ISO data I was telling about the k-means. Now, let's suppose I am having the five classes. I would like to complete in 10 iterations. And the more the number of the iterations you will give, and also it may land into the overfitting and also underfitting type of the problems. But sufficient results, 10 iterations and maximum 20 iterations will give a good amount of results. Both. It's a clustering mechanism. Any of the things when you will be doing, 10 to 20 is sufficient, good enough for doing the. This is one of the example which 1 to 5 classes, 11 iterations, and 5 for change and threshold. 5. It is also another example for the ISO data clustering. When I am having the more number of classes, the object identification will become more complex and it definitely requires an image analysis. But when I am restricted to the minimum number of classes, it is more easier for distinguishing what are the types of features I am having. So I will show one of the thing in the QGS with respect to the classification. QGS offers you doing the supervised and unsupervised classifications. But only thing what is required is it has got a plugin. Let's suppose I am going to plugins and then manage and install plugins. And then if you type here semi, there comes a plugin called the semi-automatic classification plugin. So you need to install this plugin with the latest version of the Python. But the problem in this one is now in this installation, we happens to have the latest version of QGS, but the Python happens to be a older library. That's why it's giving an error. Semi-authentication warning, Python library is outdated.
So you need to have the both the higher versions to run this. But anyway, because this is not running, I also brought the one of the video which will shows you how you can do a classification for a supervised image classification. or the AI algorithms what you are going to apply are not going to be the ultimate things. So there is no algorithm which is perfect and will transfer the all the conditions. And there is a various combinations of algorithms people want will use for improving the accuracy. And similar is the case. When you use a particular type of technology, there will be is the compromise over some parameters, and it's an has got the advantage over the some other parameters. For example, to the extent I am having an GSLV, and also I am having the communication satellites and polar satellites. Polar satellites, they will be placed around 1,000 kilometers from the height of the Earth, and communication satellites, they will be placed at an altitude of 26,000 kilometers from the Earth. And in both the cases, and one compromise over the other, what has taken place. For the communication satellites, it needs to be always visible to a particular point on the ground, so that communication will happen online and real time. But for the polar satellites, if I place it at such an high remote sensing satellite at a very high altitude, because of the limitations what are there in the cameras and also the lenses, the clarity of the images what you will get are not going to be sufficient for doing the analysis and also the object recognition and so on. So there, in the case of the polar satellite, it will take 90 minutes for reaching, taking one orbit around there. So every 90 minutes, it will take different parts of the Earth. And if to reach a particular point on the same, again, it may take some 10 days, 15 days, and so on, based on the temporal resolution of the satellite. But still, we'll place at a lower orbit because of the fact I want to have a clarity of the images. For the communication satellites, I will place only at a very high altitude because of the fact they have to be continuously available to a particular place on the Earth. So there is no technology which is perfect for everything, but you will compromise over some parameters over the other, which are of importance to you. Similar is the case with the AI/ML algorithms. And to the extent, to the larger extent, it is similar, and also it will be applicable in our day-to-day lives also, and which is extended to your life partner also. She is there, compromise some things for something, and you compromise some things for something. So there is no ideal solution, and there is no ideal algorithm what you can apply. And always CAML algorithms also, when you will be studying, what is which you are want to extract from using that AML algorithm, that has to you have to very clearly have to define and then have to do it. For example, I am doing a classification. I want to have an accuracy. I want to have the number of classes to be very perfectly delineated. I want to remove the effects of the combined pixels and mixed pixels, what are there in the data set. And if I impose some 5, 6 limitations or the existing methods, then I will be very clearly will be coming out what are the types of the architectures I might have to employ. So whenever formulating the problem, once you formulate the problem properly, your 50%, 90% of your solution is achieved. And if you are not in a position to formulate the problem, then the solution is a distance apart. Your problem itself is not complete. So with that, I will come to an end of this. And any of you have got any of the doubts, will be happy to answer all of you. If there is no doubts, then we'll close the session. Any of the doubts, madam?